Hello class, here we go. A very short video. I'm going to do one problem from this worksheet called Graphing Rational Functions, number 10. This is a problem I sort of intended to do in class if there was enough time, but there totally wasn't. And this was so I assigned it for homework, so I think I'll just make this quick video, post it. Therefore you can kind of check to make sure you're doing the stuff right. So sort of going over the homework kind of in advance or something. Alright, and this one you were supposed to do by yourself, so that does make it harder. Okay, let's go. It's a rational function. Here it is. It's a quadratic over a quadratic. Step one, I think, is to factor it. So alright, the top here is x plus 1 squared. Alright, so that's already kind of quite interesting. That's a new thing that hasn't happened yet. So it's kind of like a double root in the numerator or something. And then down here in the denominator, what is this? This is going to be x minus 2, x minus 1. Okay, great. Let's make a sign chart right now. And I think there are sort of two different ways of doing this. One way of making this sign chart, this is kind of my preference, but whatever, is to say, okay, look, the numerator is just always positive, except when it's 0. So if the numerator is always positive, then it's just always positive. So it's playing no role whatsoever in determining the sign of this rational function. Therefore, the only thing that matters is 1 and 2. Because that's a quadratic down there, the sign chart for this quadratic will be plus minus plus because it's a positive coefficient quadratic. So that's the entire sign chart. If you like that, then great. Some people don't like that. Some people feel that the number -1 should get some kind of mention. Alright, if you feel that way, then here's another way of doing it. This is just a matter of taste. You can add -1 to your sign chart because, after all, something's going on at -1. I mean, in fact, this function is 0 there. But what matters is that there is no sign change at -1. Because this is a double root, the function is not crossing, because there's a double root here, I guess maybe the thing to say is that the corresponding polynomial, after all, that's the way I taught you to make these sign charts, is to imagine the corresponding polynomial. And what does this polynomial look like? Well, it is a quartic with a double root at -1. So that's the extent to which it kind of matters that you already understand polynomials, because this double root at -1, what effect does that have on sort of the shape of this quartic? Well, we kind of know this quartic is going to have m behavior positive. It's going to go down like this, but it's not going to cross, right? So chop, chop, chop. Alright, so you do have to kind of understand what's going on here, I think, to be able to consistently make these number lines. And what's going on here is that, yes, a function will change sign at a single root, a polynomial function, but a function will not change sign at a double root. And so, you know, then there's this function being a quartic. If you're making the sign chart this way, you're essentially thinking of all 4 of these things as being there. So it's kind of like you're picturing this quartic, and it should be plus, plus, minus, plus. Okay, so if you like to do it this way, I guess it doesn't matter which sign chart you make. They're both saying the same thing. This one is just reminding you that something's going on at -1. In fact, it's 0 there, but there's no sign change at -1, so that's kind of important. Okay, whew, having done that, let's just do this problem. I think it's pretty straightforward. There are roots. Yeah, there is a root. -1 is a root, so I'll just say, you know, x equals -1, and it's a double root, as I've been saying. So that's somehow going to be important when you make a graph. What else? If I plug in numbers near 1 or 2, things are going to kind of explode. So I have a vertical asymptote at x equals 1, and I also have a vertical asymptote at x equals 2. Is there a horizontal asymptote? Yes. Based on the discussion from class, I think that it will be 1. The end behavior will be 1. But I think the best way to see that, this is the very last thing I did in class on Thursday and Friday, is to do polynomial long division. And I'm really going to just kind of insist that you do polynomial long division whenever you can. And whenever you can means whenever the degree of the numerator is greater than or equal to the degree of the denominator. This is quadratic over quadratic, so we can do polynomial long division. Let's go. This is x squared plus 2x plus 1 divided by x squared minus 3x plus 2. And okay, let's do it. How many times does this go in here? Yeah, it just goes in once. So then I get x squared minus 3x plus 2. I subtract 2 minus negative 3 is 5x minus 1. Okay, so the doing the polynomial division is not hard. And what does it mean? It means that I can write this function as 1 plus 5x minus 1 over x squared minus 3x plus 2. Okay, and now what's happened here are sort of 3 separate representations of this rational function. There is the original representation, useful for certain things, such as coming up with the y-intercept. What is the y-intercept? That's just going to be the value of the function when x is 0. Well, if I'm going to plug in 0, the most convenient form to do that in is this form. And when you plug in 0, you just see immediately that you get 1/2, so that's kind of like a free point. You have this form, the factored form. Okay, well that's super important because that tells me when my function is positive and when it's negative, and where my vertical asymptotes will be and where my roots are, so that's certainly very important. But this is also important, this form. And I think this is important, this form of representing the rational function is important for end behavior reasons because, as I said in class, as x goes to infinity, now it's sort of very obvious to me that this function goes to 1. Because this is a quadratic down here, this is a linear function up here. A quadratic function will eventually, and that's what we're talking about as x goes to infinity, will dominate over that linear function. And to such an extent that this, that 5x minus 1 will be negligible as compared to x squared. If x is 1,000,000, for example, that's roughly 5,000,000 up top, but that's roughly 1,000,000 squared on the bottom. So that's roughly 5 over 1,000,000. That's almost nothing. And as x gets bigger and bigger, this whole thing just gone. And so it's clear that this function is going to 1, and it's also clear that as x goes to infinity, as x goes to negative infinity, that this function is going to 1. Okay, so we have a horizontal asymptote at y equals 1. But the other thing that I get from this representation is the answer to the question of when this function is crossing its asymptote. If there's a horizontal asymptote of y equals 1, I want to know when is the function equal to 1. Well, if you ask when is this function 1, since this function is 1 plus some stuff, the only way this function is going to equal 1 is if the stuff is 0. And so the only time we get across is when that numerator is 0. And that numerator will be 0 in this case when x is 1/5. And so what we get out of this information is that f crosses the line y equals 1 at x equals 1/5. So at the point 1/5 comma 1 will be a point on my graph. And it doesn't cross anywhere else. Okay, so knowing that I have a double root at x equals -1, knowing these vertical asymptotes, knowing the y-intercept, knowing that I have this horizontal asymptote, knowing that there's this one place where the function crosses, having my sign chart, now this should be kind of, easy to make the graph. What does the graph look like? Well, let's try to do it right now. Let's see. -1, 1, 2, stuff like that. Okay, at 1, this thing is kind of blown up. At 2 as well, it's kind of infinite. What else? The line y equals 1 is a horizontal asymptote. And then there are a couple points that I know. One point is -1, that's a root, in fact it's a double root. And then I know at 1/5 comma 1 I have a point. Boom. Okay, and now we will just connect the dots. So, What is the left end behavior? Where am I when x is negative infinity? Well, I know that when x is like negative a million, I'm very, very close to the line y equals 1. Now, it's kind of hard to know whether I'm above or below that line, and just assuming for the moment that I care about that, how can I answer that question? Well, if I was above the line, then I would eventually have to cross it in order to get to this point, negative 1, 0. But I know I don't cross it over here, because I can see from this representation that the only time that this function crosses the line y equals 1 is when the function equals 1. And the function can only equal 1 when the remainder is 0, and the remainder is 0 only here. So it crosses here and nowhere else. That means it must start below that line y equals 1, and this is a root. But it's a double root. So maybe to kind of follow up on our conversation from last class, I can now sort of say, I don't usually do this, but you can, when x is about negative 1, what can I say about this function? Well, if you plug sort of negative 1 in here, you get negative 3. And if you plug negative 1 in here, you get negative 2. So those multiply to be 6. And so I say, when x is negative 1, this function is approximately 1/6 x plus 1 squared. In other words, this function is locally quadratic. F is locally quadratic near sort of at x equals negative 1. This is going to look, if you zoom in and zoom in on this rational function, it's going to look pretty much like a polynomial here. Specifically, a quadratic polynomial, which is kind of 1/6 as tall as usual. And so what we're expecting is something kind of like this. Okay, so double root action. This is consistent with my sign chart and everything I know about polynomials. Okay, and now we just finish it off, right? I'm positive all the way up until 1. So, I forgot to add in that I know I have this one more point here, this Y-intercept, so Jean, and now what happens is I stay positive all the way until 1, and at 1 this function is like infinite, so something like that. Now between 1 and 2 this function is negative, and it's sort of negative huge just to the right of 1, and it's going to be still negative huge just to the left of 2. And so it just kind of draws something like that. More on that in a second. And then when x is a little bit more than 2, this function is still going to be infinite, but now it's going to be infinite big. And now, does the function, what does the function do from 2 on? Well, the end behavior is 1, and I know it doesn't cross, I know it does, it's kind of just a little messy. I know it doesn't cross the asymptote ever again over here, because it only crosses here. And so now if we're going to sort of label things kind of nicely here, I have this root at negative 1, 0. I have that point, which is 0, comma, half, and I have that point, which is 1/5, comma, 1, and that's pretty much it. I think the only thing that bothers some people is the just extreme casualness with which I just draw this kind of hump here, and it's totally not accurate, and I agree. So I just want to say that if it makes you feel better to call this kind of like a sketch instead of a graph, it's kind of like a sketchy graph, maybe is what we should call it, because it's a graph which is very accurate with respect to certain things. It's accurate with respect to roots, with respect to the y-intercept, with respect to where we cross the horizontal asymptotes. It's accurate with respect to whether it's positive or negative, but it's not accurate with respect to where this relative maximum is. And I think that's just okay for now, because this is still just pre-calculus, and it's really calculus which is required to answer questions like, where is the relative maximum of this little piece of this rational function? And I have no particular reason to assume, by the way, that this is going to be symmetric. So it's not even like I could just plug in 3 halves By the way, if you do plug in 3/2, you're going to get a number which is, I think it's quite big, right? I should probably stop this video, but if you plug in 3/2, what do you get? Let's see, on the top you get 5/2 squared, so that's like 25/4, and on the bottom you get, what is that, -1/2, but then positive 1/2? Let me just double check that, -1/2 and positive 1/2. So that's -1/4. Okay, so actually you get the nice kind of round number, -25. Alright, so f of 3/2 is -25, assuming I did that correctly. And that might shock you. What that means is that actually this piece is probably like way down here, sort of off the scale or something like that. I just don't care about that right now because yeah, I just plugged in that number. If I really craved accuracy, that would be something nice to know. But really, all that I care about is that the piece in between 1 and 2 is down there below the x-axis, and it's kind of approaching -infinity just to the right of 1 and just to the left of 2. But where this piece actually lives, I'm gonna kind of leave that for calculus. And I don't think that 3/2 comma -25 is necessarily the relative max anyway either. It might be, but it might not be. Okay, whew, that's it. So this is the sort of expectation. You do polynomial division, you sort of write down the properties, you make your sign chart, you get your graph ready, you play connect the dots, and there it is. Of course, you can check these on Desmos or something like that as well. Okay, hopefully this was helpful. Goodbye.